as well that there should be, the United States don't have to win the war. It's enough to create insecurity around the borders of potential rivals. Take China and take all their situations that are in a large extent either inspired or supported by the United States. Take Russia and, take with their areas of Ukraine, Southeast Balkans, or now the Middle East. So I would say on the one hand, United States are benefiting from that, but taken there in a way lost the initiative. This could be damaging to their role because for them at the same time of putting their rivals down, it is important to still preserve this leadership role and the role of mediator or the one who can sort things out. But in this case, I would say Cold War is certainly, or let's say confrontation is evolving, but I would say it is not, it won't bring any good to the United States in this very case. So I would suggest, and I would say we have to talk and we have to start talking. It's not the Russia of the early 90s or late 80s, and we don't have China of their 80s, and those are serious countries, and I think America has to start taking it seriously.
Of course, Ambassador Volker, that is an analogy that the Prime Minister of Russia made, but do you think there is much danger of much sharper opposition between Russia and the West, especially the United States, even on this issue of Syria?
So your question about a new Cold War and about the comments by Prime Minister Medvedev, I don't believe that over Syria there is such a risk. The Syria conflict has its own drivers, its own issues. Certainly, different countries have different interests. I disagree with our Russian colleagues saying that the U.S. seeks instability. Just the opposite. I think the U.S. is looking for a long-term, stable, and secure solution, but also one that respects the interest of all the Syrian people, not just the Alawites. That being said, I think the issues of a new Cold War or confrontation between the U.S. and Russia or the West and Russia have more to do with Russia's actions in Europe. Here we've seen Russia invade two of its neighbors, annex territory, rebuild its military forces, violate countries' air and sea space, threaten nuclear strikes. And this is something where NATO and the U.S. have now begun to respond by reversing the decline in their military capacity in the area. That's something to watch. I think that's what President Medvedev was talking about. And I think here it is Russia's own actions that have brought this about. I hope that this does not lead to a greater confrontation, but at the same time, it is an obligation of the United States and NATO to defend their territory, should it ever be attacked.
Mr. Ye, danger of a Cold War?
In this part, I will agree with the ambassador in DC. Actually, I won't say this, the crisis in Syria is because of the new Cold War. It's because of the field of the two world giant power, because they are failed to manage the situation, failed to solve the problem. But it's not good news for all of us, because even the Cold War is an order, international order. But if they fail this order in the chaos in any country, that means we are incapable to run the situation.
Can you, Mr. Ye, coming from China, give us 15 seconds to illustrate the role of China? After all, China is a world power now.
No, I don't think we are capable to solve the situation in Syria. This beyond the capacity, yes, in this part.
I see. Okay. Ye Hailin here in Beijing with us, Victoria Panova joining us from Russia, and Ambassador Volker from the United States. Thank you so much for the three of you for being with us. Really appreciate it. Stay with us here on World Insight. We got our final segment coming right up. A remarkable discovery. After decades of searching, scientists have finally found proof of gravitational waves. But what does that actually mean for science or the average layperson?
From emerging powers to expanding partnerships, from fighting poverty to combating climate change, booming economies, war-ravaged nations, and everything in between. capture the changes affecting the most dynamic and diverse continent on the planet, taking you beyond the headlines to the people and their stories. Asia Today, delivering Asia to the world.
Welcome back. You're watching World Inside on CCTV News, coming to you live from Beijing. A century ago, Albert Einstein hypothesized the existence of gravitational waves, ripples in space-time that dash across the universe at the speed of light. Last Thursday, scientists announced that they have finally observed the elusive waves directly. Experts say that this discovery could open the door to an entirely new way to explore the cosmos. Let's take a look.
A big bang in the field of astronomy.
Ladies and gentlemen, we have detected gravitational waves. We did it.
At a press conference in Washington last Thursday, physicists from the Ligo Scientific Collaboration and Virgo Collaboration teams announced the discovery of gravitational waves.
So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago.
Gravitational waves were first proposed by Albert Einstein a century ago as a key prediction of his theory of general relativity. They are concentric ripples that squeeze and stretch the fabric of space-time. In certain circumstances, the movement of immense mass would cause gravitational waves, but most are so weak that they have no measurable effect.
So on September 14th, 2015, the two LIGO observatories in Hanford, Washington and Livingston, Louisiana recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up.
This observation is the climax of a century of speculation, 50 years of trial and error, and 25 years perfecting a set of instruments. It signals the opening of a new window onto the universe.
Results confirm several very important predictions of Einstein's theory of general relativity. It confirms the existence of gravitational waves directly. Gravitational waves provide a completely new way of looking at the universe. The ability to detect them has the potential to revolutionize astronomy.
The Laser Interferometer Gravitational Wave Observatory, LIGO, is a large-scale physics experiment and observatory to detect gravitational waves. More than 1,000 scientists involved in the project come from 15 countries around the world. A research team from Tsinghua University is also a member in this project. The research and observation of gravitational waves is growing globally now. A new proposed collaborative project between LIGO and India is underway. China's scientists are also working on a project called Tianqing. The human dream of exploring the universe has always marched forward.
Yes, marching forward to analyze its significance and what does it mean for us, particularly for the near future. We're joined here in the Beijing studio, Mr. Zhang Fan, who is the Associate Professor at the Gravitational Wave and Cosmology Laboratory at Beijing Normal University. My first time to understand there's a laboratory like that in Beijing. Wonderful. Great to see you here. Meanwhile, joining us from Princeton, New Jersey, we're having Mr. Robert Digraph, who is the Leon Levy Professor and also Director at the Institute for Advanced Study. Welcome as well, Mr. Digraph. First of all, I want to ask...
It's wonderful to be here.
Great to have you, sir. Ask the two of you, who are the experts, what exactly is the significance of this latest development? Of course, we've been hearing numerous experts talking about the significance, but still, sometimes it's a little bit confusing. So let me have some very clear words from you first. Robert, you want to go first?
Oh, yes, sure. I think it's hard to underestimate how important this is. Einstein learned is that apart from light, there's another way to look at the universe, and that's through space itself. Space can curve, that's what we call gravity, but it can also vibrate and it can produce waves. And so this moment in the history of science, I think, can be compared to when Galileo first pointed his telescope and looked at the moon and the stars. We actually have a new way to look at the universe, basically by observing ripples in space itself. And this will be a tool for us to observe anything that doesn't emit light, whether it's black holes, whether it's the beginning of the universe itself. We basically have a totally new way to observe the universe, and I think that's extremely exciting. I think we all sometimes think, I just wish I was alive when the great revolutions of science took place in the 17th century or in the time of Einstein. We are living actually in a revolution right at this moment. We are learning how the universe works, how it was made, and where it's going, and that's terrific.
Well, Mr. Zhang, I'm sure you are just as excited as Robert, but Fan, tell me, what would that mean for the layperson? Yes, you would say, besides the electromagnetic waves we have used before to discover further about the universe, we now have a new tool. But how much would this new tool help us? Do we really know? Or are we overexcited already before we know anything further about it?
No, we cannot be overexcited about this. So as Robert mentioned already, so this is a completely new window on the universe. So astronomy is one of the first sciences we have as a human race. And from the beginning, we only had one channel to look at the universe, and that's electromagnetic waves. And now we have gravitational waves and also neutrinos coming up. So there's we're not just doubling, we're tripling the ways we look at the universe. And also, for layperson, you know, if you're a fan of science or even science fiction, this will interest you. It's the one thing, the basic fundamental science. And in terms of practical usage, I guess that's the question that you're really asking. You know, if you, I'll go crazy first. So if you watch Interstellar, the movie, right? So there's a gravitational wave is used for interdimensional communications, and also there's a really famous Chinese science fiction called Three Body. And in there, gravitational waves is also used for communication. And also...
But that's science fiction. Come on. You cannot use science fiction to prove that the possible development you are going to have in the future. In real science, this is different.
In the future. But, more immediately, stuff that's... The spin-off technology of Ligo can be used immediately in our to improve our daily lives. For example, so Ligo is basically a measuring device for distance, a very accurate one, which means the whole thing has to be stabilized against movements of the ground. You can't jiggle like that. So there is something called the vibration isolation system developed for Ligo, which is the most advanced thing in the world. And when can you use that thing? For example, if you're doing microchip manufacturing, when you're making those tiny little conducting lines in there, nanometer lines, you really don't want the workbench you're working on to jiggle like that. There's no way you can achieve any precision that way. So, for example,
and that is only one of those enormous amount of examples that how much of this further science contribution, science discovery could contribute to the daily life of the layperson. Having said that, though, Robert, would you like to explain to us how much potential and what is the speed of research we are having? I mean, it already takes 100 years after Mr. Einstein come up with this general relativity theory. So how much would this technology or this new discovery really help us? In what speed?
Well, first let me remind you, when Einstein made his theory of relativity, he didn't dream that we would be using it every day when we use our GPS. Without Einstein relativity theory, we would mislocate our directions with a few kilometers every day. And so what we've seen, that technology has advanced to such a level of sensitivity that all the intricate details of nature and of how the universe works will start to matter for us. So I'm sure that in 100 years we will have terrific applications of this technology. But I think more important is that we are getting a sense of what is the universe we are living in. And up to now we have basically been blind to many important developments. It was a great shock for all of us when the first measurement came in, that it was this extremely violent collision of two black holes. These black holes apparently are out there. They are determining the universe. In fact, they're determining how we all came to being. And so I think apart from the terrific technological developments, the most important thing is we get a sense of where we are. What is the universe that we live in? And we also are realizing what we do not know. It's just, if you can't see it, it doesn't mean it's not there.
Right.
And we basically got another pair of eyes to watch the universe.
Right. But Robert, may I continue to ask you, because it really takes us a long time to find the electromagnetic waves to begin with. And then it also takes us 100 years to prove what Mr. Einstein said already about the general relativity theory. And this specific gravitational waves is a new discovery. However, how many other discoveries we still need to have before we understand really the universe? So what I'm trying to say here is, Robert, how much do we know about the universe to understand that gravitational waves is really contributing to our understanding of the logic, the real logic of the universe?
Well, it's important to emphasize this is the first of a long series of discoveries that will come fast. Gravity is the perfect way to study the universe, because Einstein told us gravity measures anything that has mass and anything that has energy. So there's no way you can hide for gravitational waves. It's a completely comprehensive view of the universe. And we know that there are many elements in the universe we do not understand. Roughly we understand only 4% of the content of the universe. 96% we call dark matter, dark energy. We have basically very little idea how the universe was born because we cannot see the very beginning of the Big Bang. Gravitational waves have the property to pass through everything, so they are the perfect way to measure all these phenomena. And the great thing is that there are many experiments going on. This first discovery was basically made before the experiment was turned on. It was still in the experimental run. It's like you go on a safari and already in the parking lot you see a wonderful animal. So I think we'll see very rapidly in the coming years many, many exciting discoveries that totally will transform our understanding of the universe. And in fact have the potential to ask and answer the really deep questions. In particular, I think the biggest question of all, how did it all start?
Right. But how many animals, the beautiful animals, do we have to see in the parking lot in order to figure out?
Quite a few, actually. There are a lot of things we don't know about the universe. So first of all, well, just theory-wise, general relativity and quantum mechanics still doesn't work together. More practically, as Robert just mentioned earlier, 95% of the universe is something we don't know. For example, I want to follow up on the dark matter thing. So dark matter is something that's in the universe that doesn't interact strongly with other sources, other sort of forces apart from gravity, which means it doesn't emit light. It doesn't emit much light.
Right.
So it's very difficult to observe them using the traditional methods. But gravitational waves opens this completely new window where we can actually look at those things, see how they evolve, and really understand what they are. We don't know what they are, basically. Our standard model for particle physics don't have them. So that's so basically we now have something to look at them.
Right.
That's a jump That's not just gradual change.
That is exciting, but we've seen some interesting development. For example, in the United States, that's where the announcement was being made.
Right.
We also have these kinds of LIGO systems inside India, Italy, and also Japan at the moment. And in 2 years, some say India is also a possibility. And some also suggest in China, as you already got a lab in Beijing Normal University regarding gravitational waves. So what is the latest development here in China? What is the role of China contributing to the overall world research?
Okay, so China.
Big announcement, it seems like.
Right. This thing. I was tasked by my department to flash this in front of the camera.
Okay. All right. Enough motion.
So that's so there's a lot of interest in China in gravitational waves. So I flashed that thing because last year we had organized a meeting that talks about the possible technology for next generation detectors. That happened in China, and the result is summarized in this particular journal. You can look it up online.
What exactly is the role? What exactly is the role?
What exactly is the role? So basic summary, we have very limited role. So we have, on the theory side, we have some people, tens of people, not hundreds of people, in Tsinghua, obviously, Beijing Normal University, and some other universities, Huazhong University, Zhongshan, and Chinese Academy of Sciences. But most of the people work on gravitational wave related topics, not 100% on gravitational waves. That's a stereotype. On the experiment side, we're very lacking. So basically, there's no current dedicated gravitational wave observatory currently operating or under construction in China. I don't think there is any preliminary study that's currently being properly funded. But nevertheless, people have been making proposals. They've been making preliminary studies. Tianqin, that's mentioned in the short piece earlier, is spearheaded by Zhongshan University and Huazhong University of Science and Technology. There are other things like Chinese Academy of Sciences is doing.
I see. Let me ask you, is it possible to have international cooperation involving China? Is China willing to join? Are others willing to have China join?
So Tsinghua is already a member of Ligo. So, and my university myself is part of the Japanese detector called Kagra. So yes, on the scientist level, collaboration is greatly welcomed, and we feel very, very welcome as well. Well, of course, when things come up to political level, then hurdles may arise. But we haven't gone to that stage yet.
Okay. Robert, do you think we are facing the danger that maybe at the political level in the near future, as more discoveries are being progressed, there might be difficulties for countries to cooperate?
No, I think it's the opposite. I think actually this is a wonderful opportunity to collaborate. And I think actually there's a very good reason for this. We need more gravitational wave detectors because only with many detectors can we actually pinpoint where the gravitational waves are coming from. And so the strength of this experiment is really to combine various instruments at various places in the world. And only then we can actually also combine gravitational waves with observations in visible light and radio waves to actually see what's going on.
Right.
So I think this is a terrific opportunity to really build a laboratory that's worldwide and where the various countries are collaborating. And China has such an incredible knowledge in terms of the technologies that are needed for this. I think would be a perfect fit for China to join this international collaboration.
All right, before we go, I want to have one sentence from each of the two of you about what exactly do you think would be the most exciting thing that we discover gravitational waves for us to see about the universe? Fan? One sentence.
I'm an astrophysicist, so I want to see I want to study the space-time dynamics near the black holes. How do they evolve?
All right, Robert.
I think I want to understand why and how black holes have formed at all in the very beginning of our universe. And I think we'll get an answer pretty soon.
Oh, all right. I'm looking forward to that pretty soon. Wow, that sounds already very exciting. Robert Digraph and John Fan, thank you so much, gentlemen, for joining us. When we are finding it really soon, we are going to invite you guys back again into our studio. Thank you so much.
Thank you for having me.
Issue of Syria.
So your question about a new Cold War and about the comments by Prime Minister Medvedev. I don't believe that over Syria there is such a risk. The Syria conflict has its own drivers, its own issues. Certainly, different countries have different interests. I disagree with our Russian colleagues saying that the U.S. seeks instability. Just the opposite. I think the U.S. is looking for a long-term, stable, and secure solution, but also one that respects the interest of all the Syrian people, not just the Alawites. That being said, I think the issues of a new Cold War or confrontation between the U.S. and Russia or the West and Russia have more to do with Russia's actions in Europe. Here we've seen Russia invade two of its neighbors, annex territory.
Mediator or the one who can sort things out. But in this case, I would say Cold War is certainly, or let's say confrontation is evolving, but I would say it is not, it won't bring any good to the United States in this very case. So I would suggest, and I would say we have to talk and we have to start talking. It's not the Russia of the early 90s or late 80s, and we don't have China of their 80s, and those are serious countries, and I think America has to start taking it seriously.
Of course, Ambassador Volker, that is an analogy that the Prime Minister of Russia made, but do you think there is much danger of much sharper opposition between Russia and the West, especially the United States, only even on this?
Build its military forces, violate countries' air and sea space, threaten nuclear strikes. And this is something where NATO and the U.S. have now begun to respond by reversing the decline in their military capacity in the area. That's something to watch. I think that's what President Medvedev was talking about. And I think here, it is Russia's own actions that have brought this about. I hope that this does not lead to a greater confrontation, but at the same time, it is an obligation of the United States and NATO to defend their territory, should it ever be attacked.
Mr. Ye, danger of a Cold War?
In this part, I will agree with the ambassador in DC. Actually, I won't say this, the crisis in Syria is because of the new Cold War. It's because of the field of the two world giant power, because they are failed to manage the situation.
As well, that there should be the United States don't have to win the war. It's enough to create insecurity around the borders of potential rivals. Take China and take all their situations that are in a large extent either inspired or supported by the United States. Take Russia and, take with their areas of Ukraine, Southeast Balkans, or now the Middle East. So I would say on the one hand, United States are benefiting from that, but taken there in a way lost the initiative. This could be damaging to their role, because for them, at the same time of putting their rivals down, it is important to still preserve this leadership role and the role of...
Solve the problem, but it's not good news for all of us, because even the Cold War is an order, international order, but if they fail this order or the chaos in any country, that means we are incapable to run the situation.
Can you, Mr. Ye, coming from China, give us 15 seconds to illustrate the role of China? After all, China is a world power now.
No, I don't think we are capable to solve the situation in Syria. This beyond the capacity, in this part.
I see. Okay. Ye Hailin here in Beijing with us, Victoria Panova joining us from Russia, and Ambassador Kurburka from the United States. Thank you so much for the three of you for being with us. Really appreciate it. Stay with us here on World Insight. We got our final segment coming right up. A remarkable discovery.